All right, this is a lecture dealing with Bernoulli's equation, which governs the flow of water through a pipe, perhaps a tapered pipe, one that is narrowed or widened at various places along its length. I show a pipe that's tapered at the right end. At the left end, not shown, is the pipe that interfaces in this location. Fluid, in our case it will always be water, is flowing at this location with speed V1 at this first location. The cross-sectional area of that slice is symbolized as A1. The center of the pipe is a height H1 above some reference ground. The pressure at that location in the pipe, in the fluid, in the water is P1. We have similar variables at the right end of the pipe, which has a cross-section A2. The speed of the water at that point is V2, and the pressure in the water at that point is P2. The center of this portion of the pipe is at height H2 above the ground. Bernoulli's equation is shown here. The sum of these three terms on the left side of the equal sign is equal to the sum of these three terms that are identical to those three, except for a change in the subscript from 1 to 2. A second equation, which is not officially a Bernoulli's equation, is an equation you would have seen earlier if you've looked in the chapter notes. It's the volume flow rate conservation equation. I will not discuss it in this lecture. It is discussed comprehensively in the lecture notes. The diagram displays 8 different variables. 4 on the left side of Bernoulli's equation and 4 on the right side. I'll count them now for you. 1, 2, 3, and the area A1 is down here. So associated with the left side of this pipe through which water is flowing, there are 4 variables that will often be dealt with in our solution of a Bernoulli's equation problem. Count them again. P1, V1, H1, and A1. 4 equations for the left side, 4 variables I meant to say, and 4 on the right. In order to solve a typical Bernoulli's equation problem, you have to have as many equations as you have unknowns. In the event that there is a single unknown whose solution is looked for, you need only one equation, one of these 2 equations. In the event that there are 2 unknowns that you must find, you will need 2 equations. Bernoulli's equation and the volume flow rate conservation equation. In the next lecture, I'll work a problem in which both equations are needed because there will be 2 unknowns. One from the left side and one from the right side. Or perhaps we'd work a problem in which there are 2 unknowns over here, or perhaps 2 unknowns here. A typical Bernoulli's equation problem involves not a horizontal pipe that's tapered, but a tank of water. Water is flowing out of a faucet or drain pipe. That's analogous to water flowing out of the right end of this horizontal pipe. water at the other end is flowing downward. We'll work a problem involving a horizontal pipe configuration and leave this sort of problem for the lecture notes.